I do want to welcome everybody on behalf of the Advanced Carbons Council. If you're not familiar with who we are and what we do, we started as the Graphene Council more than 10 years ago. We've expanded to the advanced carbon sector to include materials like what you'll hear about today, carbon nanotubes and other advanced carbons. We are a global neutral trade association connecting more than 40,000 individuals who have an interest in advanced carbons and how to use them in engineered solutions, which you'll hear a lot about today in today's presentation. I'd like to officially kick off today's webinar and introduce our speakers representing DexMat, a valued member of the Advanced Carbons Council, talking about the materials that they create and how they can be used. We're joined by Dmitri Tsentalovich, who is the co-founder of DexMat and the CTO, and he is joined by Oliver Dewey, who is the process development engineer for DexMat. And with that, I'm going to hand over to the gentlemen to further introduce themselves and to share with us an excellent story that DexMat has about the materials that they've created. So thank you.
Sure. Thanks, Terrence, for that great introduction. And we'd like to thank the Advanced Carbons Council for giving us the time to speak today. Before I move on to our introduction slide, I just want to give a quick nod to some intrepid graduate students at Rice University who have a light bulb installation that we've put as our background here. It's really impressive when you see it in person. They're using very thin Galvorn conductors to create the appearance that a very large light bulb is suspended in thin air. You can check out our blog. We'll share some links to that. It's a fun project that they showed off the lightweight and electrical conductivity and strength of Galvorn. All right, so my name is Oliver Dewey. I'm the process development engineer at DexMat. I have a PhD in chemical engineering from Rice University from the group of Matteo Pasquale, the same academic lineage as Dmitri Tsentalovich. Dmitri actually taught me how to spin carbon nanotube fiber at the beginning of my PhD, and then when I walked out the door of Rice, I quickly walked in the door at DexMat. My realm of expertise is primarily fiber spinning and scale up and tailoring properties of the fibers that we make to various applications to meet the needs of our customers. So I'll hand it over to Dmitri.
And I'm Dmitri Tsentalovich, co-founder and CTO of DexMat. I also have a PhD in chemical engineering from Rice University, where the technology that DexMat is now developing for making carbon nanotube fibers and other materials that we brand Galvorn. I've had over 15 years of experience in developing and advancing carbon nanotube-based materials. At DexMat, my role has been focused on building the technical team as well as leading the product improvement, production scaling, and cost reduction efforts that we've been undergoing. I'm also the primary technical contact for our most strategic customers, and I'm really excited to share Galvorn's revolutionary potential here with you guys today. You want to go to the next slide? So conductive materials are a key bottleneck in massive industries that are multi-trillion-dollar global industries. And our economies are becoming increasingly digital, electrified, and reliant on AI, all of which demand high-performance conductive materials. Today's conductive materials, like copper, aluminum, and steel, have significant limitations. They're heavy and bulky and typically lack the strength and flexibility that's truly needed for next generation applications. Furthermore, much of these metal-based materials are complicated by the fact that they are concentrated in specific regions, leading to vulnerabilities and geopolitical tensions. And also, they have a massive environmental impact from having to mine these types of materials. So there's an urgent need to find a new class of conductive materials that can not only meet the increasing demand for conductive materials, but also overcome the hurdles associated with the environmental impact of current conductive materials. Galvorn is the strongest, lightest, and most flexible conductive material on the planet. It's based on carbon nanotube fibers, and it is 80% lighter than copper while being 50 times stronger and 1,000 times more flexible. Galvorn was initially developed from Nobel laureate at Rice, technology developed by neurolawyers at Rice, and has been funded by NASA and the DoD and the Air Force for applications primarily focused on high performance materials in space and aerospace. But DexMat has been increasingly scaling up and reducing costs to the point where we're now starting to also develop Galvorn for terrestrial commercial applications here on Earth. And I'm going to turn it over to my colleague Oliver Dewey here, who's going to give you a bit more perspective on the properties as well as the process that we use to make Galvorn.
Yeah, thanks, Dmitri. So Galvorn outperforms all other conductors when we look at our performance advantage here. So because Galvorn is comprised of densely packed and highly aligned carbon nanotubes, it's extremely lightweight. It's very, very strong. It's thermally conductive because it's pure carbon. It's corrosion resistant, surprisingly cut resistant. It outperforms Kevlar, Dyneema in impact and lateral cutting tests, which we have kind of academic papers that other groups have done demonstrating that. And a key difference with other conductive materials is that it's sustainably produced, and at end of life, it's 100% recyclable. If you look at the Ashby plot that we have on the right, we're comparing the strength kind of as a stand-in for the mechanical durability of conductors versus their specific conductivity, which is the conductivity of the conductor normalized by its density. And you can see that Galvorn kind of occupies a space of its own up in the top right of the plot, where it is both strong and electrically conductive, rivaling copper in terms of its specific conductivity, but far outperforming, even specialty electrical conductors like Aerocon, other carbon nanotube fibers that are available on the market, and nickel-coated carbon fiber. We're going to share a link to our spec sheet so that you can check out the properties of all of the Galvorn form factors that we have available. And of course, if you reach out to us, we'd love to hear from you and discuss how we can adapt Galvorn to your needs and your applications. We also have a scalability advantage. So right now we're on track to reach 3 kiloton scale within 5 years. Since Galvorn was introduced or invented, we've scaled up our production capacity 3000x, and we've reduced our production costs by 99.5%. We're really seeing exponential growth in how we've been able to scale this technology. And the key comes down to the way we produce our fiber. So we use a solution spinning process that has unmatched properties at the output due to the alignment and packing that I mentioned earlier. And because it's a wet spinning process, it's highly scalable. So what does this look like? We take raw carbon nanotubes. We can work with a variety of feedstocks from a variety of manufacturers. We dissolve them in a solvent to form a liquid crystalline solution in which the carbon nanotube molecules will spontaneously align. We create bulk alignment in these solutions by extruding them through a spinneret, and we densify them in a coagulation bath. So that part is standard solution spinning processes. We collect the material on a rotating drum at the end of the process. So this technology is already commercially proven at 100 kiloton scale, and it's used to produce I won't call them household names, but industrially household names like Kevlar, rayon, viscose, things like that. It's really easy to scale our process because if you need more fiber, you can essentially poke more holes in the shower head that we're showing in panel 2 here of our process. And then finally, our product is typically a fiber tow of parallel filaments, anywhere from 1 to potentially thousands of filaments as we scale up our fiber spinning technology. And then, as I mentioned, at the end of the process, we can take those fibers at the end of life of a product, rip them out of whatever you've got them in, and put them back in at the beginning of our process and make fiber anew with same properties as we produced at the initial process. Again, we've got an article here that you can read about that based off some research at Rice University. And then to put a point on it, fiber wet spinning is proven at scale. So if you think about viscose, this is the most used man-made cellulosic fiber. About 80% of all man-made cellulosic fibers in the world are viscose, and it's produced at amount of 5.8 million tons in 2021. So this is a really massive industry using essentially the fundamental technology that we have. Obviously, we have our own kind of secrets that we use to convert this with carbon nanotubes, but at a scientific level, the technology is proven, used at scale, highly cost effective. Also, when we produce carbon nanotube fiber, we're making something that is higher performing and less energy intensive, less expensive, and more geopolitically resilient than our most pervasive conductive materials, typically metals, as Dmitri was mentioning at the beginning of our talk. So here we're showing the energy intensity of production of a variety of materials, so including structural materials like carbon fiber, steel, stainless steel, automotive steel, and then conductive materials like copper. Aluminum sits in a place where it's both used structurally and in some niche applications for its electrical properties like overhead power lines. If you look at Galvorn today, we're sitting kind of in the middle here. At scale, when we use bulk production technologies, we're looking at something around putting us between copper and steel on a per kilogram basis. However, the secret of Galvorn, or the kind of secret strength of Galvorn that we don't want to be so secret, is that it is extremely lightweight. And so it doesn't take a kilogram of Galvorn to do the work of a kilogram of steel. So when you actually start putting these energy intensities on a performance levelized basis, your CO2 emissions used to make something, or the energy that you put in used to make something, goes a lot farther to get the work done. And we're happy to discuss this at length after the chat. So to kind of bring that to more clarity, we have some properties here. So at the top, we're showing specific strength and specific conductivity of Galvorn carbon nanotube fibers compared to different metal conductors or strength materials. And you can see that when we look at the specific properties, we're outperforming all of the metals in terms of strength. So if you consider how many emissions you have to make in order to do the same amount of work or produce the same or support the same amount of weight, you can see that Galvorn is far outperforming the other metals just because it's so lightweight, it's so strong, and we're at comparable efficiency in terms of production. And then in terms of specific conductivity, even though we're kind of in the middle of the pack, we're not quite at copper, we're not quite at aluminum. For specific conductivity, our emissions are still outpacing everything else, outperforming everything else. And then I want to put a point on something here, that when we look at these calculations, we're extremely conservative. So we're actually using lower strength and conductivity numbers than our material is capable of. We don't want to oversell our environmental impact, and we understand that in certain applications things need to be composited or used with other materials. So we put a little bit of a conservative number on these slides. So Dmitri, I think I'm kicking it over to you.
One thing that I would like to highlight is that we've developed Galvorn so that it can drop into existing manufacturing supply chains by making it in a number of form factors. So the base form that Oliver described that we produce is a fiber, which we can then assemble into wire or yarn, or we can also produce Galvorn in a film form factor. And then the wire, yarn, or the film can also be assembled into fabrics by weaving, embroidery, knitting, etc. The fiber form factor is useful for applications such as composites structures, where you can basically integrate it directly into CNT or Galvorn fiber reinforced composites. The wire or yarn is a drop-in for conductive wiring applications. The film so far has been primarily used for EMI shielding applications, but can also be valuable in all types of flexible electronics. And then the fabric is both for smart textile applications, but also applicable in various composite applications. And if we go on to the next slide, one pretty new and exciting application that we're developing with an organization named Tokai Rika, that's a Japanese automotive customer, is thermoelectric generator fabrics that are based on Galvorn. So there's a lot of wasted heat across a variety of industries, including automotive, space, industrial processes, and many others. And Tokai Rika is developing a thermoelectric generator fabric based on Galvorn that can harvest this waste heat and convert it to electricity. uh, in a form factor that is not possible with traditional thermoelectric generator materials, which are typically exotic materials like bismuth telluride, which also tend to be relatively toxic. And so this is right now being rolled out in kind of niche areas. And we show here a satellite. Also, you can see a picture of a cow wearing a monitor. And so this is basically for livestock monitoring with a sensor that will never die because you are constantly taking the heat from that animal and converting it into electricity as opposed to having to have a battery that needs to be changed every so often. And then if you go to the next slide, another application that we'd like to highlight that is already currently on the market with made with Galvorn materials is high-end audio cables, and a company that we've been working with named Yeti Acoustics is coined the sound that you get with Galvorn-based audio cables as magical. The reason that Galvorn works so well for audio is because you get a flat response with frequency, which is highly desirable for maintaining a good signal between your audio interface and your speakers. And so right now, Galvorn is being developed for these super high-end audio cables, but as we continue reducing the cost and increasing the scale of Galvorn, it's going to be viable to have that on all types of audio cables, and it'll also make those cables significantly lighter. So anyone who's worked in the music business and has to haul around large amounts of XLR cables will appreciate being able to have something that is made with a conductor that is almost 10 times lighter than copper. Next slide. Another application that I would like to highlight is signal wiring in aerospace. This also applies in other industries, but in aerospace, weight is particularly valuable. And Galvorn, as we've mentioned, is about 80% lighter than copper. So when you make a cable that you use Galvorn to replace the copper wiring, you basically end up getting on the overall cable almost a 50% or more weight reduction, which translates to significant fuel savings as well as potential to increase payload or range of the aircraft or spacecraft. And initially, we are really focusing on developing Galvorn wiring for drone applications because those are going to be able to be tested and rolled out into the market much faster than manned aircraft, which obviously requires years of testing and validation before they're going to fly an aircraft that has a new wiring material on it. But ultimately, there is a potential outside of aerospace for Galvorn wiring, which is lighter, more flexible, and much more durable, as well as resistant to corrosion, has a number of other advantages over copper-based wiring. Next slide. Uh, in other aerospace applications, Galvorn is also currently being explored by multiple aerospace customers for lightning strike protection. Traditionally, airplanes were made out of aluminum frames, but now the majority of aircraft are using carbon fiber composites as the fuselage and various other structural components of the airplane. Carbon fiber has much lower electrical conductivity than Galvorn, and in order to have lightning strike protection, there's usually a exfoliated aluminum or copper that's also incorporated into the bodies of these aircraft to basically deal with lightning strikes. With Galvorn, there's a potential to just make a composite that's completely made out of Galvorn fibers, which has orders of magnitude higher conductivity than carbon fibers, and therefore eliminate all the weight that you have from this exfoliated aluminum and copper that's currently being used for lightning strike protection for these type of aircraft. And another aerospace application that I'd like to highlight is that Galvorn is being used as structural health monitoring right now, primarily focused on aircraft by basically putting small amounts of Galvorn fibers into carbon fiber composites. And because they are very sensitive to changes in strain, when there's a change in the strain of that composite, there's a change in resistance of those Galvorn fibers, and that is able to be calibrated to detect any type of breaking or damage of those composite structures. And so that is currently being developed for aircraft structural health monitoring, but can also be applied to a variety of other industries, including subsea structures, uh, piping that goes kilometers down into the sea that can now be monitored with a fiber that's based on Galvorn. And with that, I think I'm just going to quickly recap all the different information that we've thrown at you and move into the question and answer portion of this segment. So, Galvorn is not just an incremental improvement in material performance, it's really a transformative material platform. It's lightest and strongest and most flexible conductive material that we currently have available on the planet. It solves critical bottlenecks in multiple industries, enables new applications while enhancing existing ones, and offers a variety of versatile form factors that can be easily integrated into end-use products while simultaneously addressing environmental and supply chain concerns. So, thank you so much for your attention. And I know we've covered a lot of ground, but Oliver and I will be happy to take any questions you might have.
Well, Dmitri, thank you very much. Oliver, thank you as well for the presentation. Really exciting development and product that you guys have created here. So there are a number of questions. If anybody does have a question and you haven't written it into the Q&A yet, now would be the time to do that. There's a couple of questions come to my mind from the beginning, kind of with the business model and how you guys are going forward. You've shown a range of applications, all of which are very exciting. Which application are you guys most excited about in terms of commercial opportunity?
So I think I can take that one. For us, it's really the aerospace signal wiring, primarily because that's the first application that can reach significant volumes of Galvorn deployed. Ultimately, we want to develop Galvorn to the point where it's going to cost less than copper. But today, we need to take advantage of the fact that we're still producing at relatively low scale, and therefore it needs to be positioned in applications where it's delivering a lot of value. And there's few applications where it's as valuable to save weight as in aerospace, and we can do that in really significant amount of weight savings when we take a cable that has hundreds of meters of it or even hundreds of miles of it on a big aircraft and replace it with a cable that is 50% lighter. That is, potentially over 1,000 kilograms of weight savings, which translates to significant fuel savings or enables different capabilities than are possible with today's aircraft.
Yeah, I would say a metric ton of weight saving on an aircraft is absolutely incredibly valuable, right? For savings. There are a couple of questions technically just to understand the process that's involved with the alignment of the carbon nanotube. So some of them are, is it from the shear stresses associated with the extrusion, or other questions about what's the mechanism for causing these nanotubes to automatically align? I don't know if that's something you can speak to.
Oliver, do you want to take that one?
Sure. Yeah, we can speak to that. So what happens when you dissolve carbon nanotubes in a solvent? They're individualized and they're very long molecules with very small diameters. And when you put molecules like that in solution, and this is similar to how Kevlar and some other materials are processed, they form what's called a liquid crystalline phase. In that phase, the nanotubes spontaneously align in localized areas. So you'll have one domain where all the carbon nanotubes are facing one direction and another domain where all the nanotubes are facing a different direction. So that localized alignment is actually done as a reduction in entropy in these solutions. And then we create bulk alignment in the solution exactly as the questioner is asking. You can shear it through a well, really, you create elongational flow through a spinneret, which aligns all of the carbon nanotubes into a single direction. Again, this is very well understood kind of fiber spinning technology when you use solution spinning, particularly of rigid rod materials.
Excellent. Thank you for that, Oliver.
Yeah.
There's another question about the thermal characteristics of the material and how does it compare, for example, in aerospace or rocketry or some other very high temperature carbon. And I can also think of specialty brakes like Formula One race cars using carbon composites for brake or silicon composites. How does Galvorn's thermal properties compare maybe to some of these materials?
Oliver, do you want to take that one as well?
Yeah, sure. So when we look at the thermal properties of Galvorn, we have very similar thermal conductivity to metals like copper, particularly in the direction of the fibers. So our thermal conductivity we've measured as high as 400 or 500 watts per meters Kelvin. In terms of thermal stability in air, the carbon nanotube fibers that we make and films are stable up to about 400 or 500 Celsius. In an inert environment, if you isolate them from an oxidizing agent, you can safely bring them up to about 1,000 degrees Celsius. So that opens up a really wide range of applications depending on what you're trying to do with it. Now there is some dependence of the electrical conductivity on temperature. So if you go very, very high in temperature, you will lose some of our electrical conductivity. But again, very, very few materials are trying to be power cables at 1,000 C. So it just kind of depends on what you're trying to do with it. To TLDR, we have a high thermal stability, high thermal conductivity, and we're happy to discuss in detail for different folks' applications to see how we can make it work.
Excellent. There are a couple of questions that I think are interrelated. So one is whether or not you guys actually make your own carbon nanotubes or source them. My understanding is you don't make the nanotubes, but you can source multiple types of nanotubes for your product. Is that correct?
Yeah, that's correct. So currently we are buying carbon nanotubes from a couple of different strategic suppliers that we're working with. In the future, we are open to the possibility of actually bringing CNT synthesis in-house, and this is very typical for companies that produce fibers via wet spinning. They'll actually produce the polymers that are used in those wet fibers in-house, but at the scale at which we are today, relative to the scale at which there's available supply of raw carbon nanotube materials with the quality and properties that we need for our process, it just makes it easier and less complex for us to purchase those materials directly. However, one thing that I do want to highlight is in the past 20 years, the improvement in both electrical conductivity and strength of fibers made from carbon nanotubes, which DexMat calls Galvorn, have been about 25% per year on average. And part of that was due to just better processing and improvements in the wet spinning technology. But a lot of it also stemmed from using better quality and higher aspect ratio carbon nanotubes. And so we think that there's still a long way to go, and the performance that we have today is good enough for a wide variety of applications, but likely over the next 5 to 10 years, we're going to get even better performance from Galvorn fibers that are going to be based on using even higher quality carbon nanotubes.
Excellent. Dmitri, thank you for that. And along those lines, again, there's a couple of questions related. People are asking, single wall versus multi-wall carbon nanotubes. They're asking about what is the ideal or appropriate length of the carbon fibers. Another one relates to how the market is growing, but points to a lack of standards. And I want to take the opportunity to point out the Advanced Carbons Council does produce for our members or non-members a carbon nanotube market report. So there's 125 companies that have been profiled that produce the carbon nanotubes. And I just want to ask along these lines, in ISO and some of the technical groups, there are some standards being revised and created for carbon nanotubes at the moment. Can you just speak to consistency in supply, or is there any obstacles to you because of a lack of standardization, or does that make sense, that question? How does that play into how you operate using carbon nanotubes as raw material? How important is it having them standardized and maybe even having better quality from the market?
I think that there are a couple of questions that you're out. So the first one is we have different grades of Galvorn that we produce, and so having more standardization would definitely make that process easier. But because we've been at this for so long, we've basically been able to survey and test materials out from uh, probably over 100 suppliers at this point, and we've found which grades are best for making the strongest fibers, which grades are best for making the most conductive fibers, etc. And so we have at DexMat already this wealth of knowledge about all the different potential properties that we can get from different types of materials. But obviously, eventually DexMat is not going to be the only company that makes high performance carbon nanotube fibers, and standardization across the raw carbon nanotube feedstock is going to enable other companies to potentially also start to compete in this space. And there are some organizations that do make fibers outside of DexMat, but they're also doing it at a relatively small scale. So I think if we're going to be replacing things like steel with Galvorn carbon nanotube fibers, there's going to be other companies that are also doing so, and I think standardization is just going to help increase how quickly that can happen.
And Dmitri, can you speak to multi-wall versus single wall? What distinction is there, and do you guys have a preference, or does that make a difference for your particular product?
Oliver, would you like to take that one? Oh, you're on mute.
Sorry, I was getting a cup of water earlier and I didn't want to disturb the conversation. Yeah, thanks, Terrence. It's a great question. We are agnostic to the number of walls of the carbon nanotubes, and of course, we're not going to disclose exactly which carbon nanotubes we use to make Galvorn. I think the biggest thing for us is that we need essentially high quality carbon nanotubes with high aspect ratios to get the best performance out of our materials.
Understood. There is a question which we anticipated about the cost, and we don't discuss pricing on these kind of webinars. They're more technical in nature, so we just encourage you to reach out to DexMat regarding commercial conditions. There was also a question about how your material might compare to a competitor. We don't really want to engage in that kind of conversation either, but I would encourage people to reach out to you, and then we will put a link in the chat at one point how to download the technical data sheet for DexMat, and encourage you to reach out to them directly. Another question, we have quite a few questions here. We'll get to as many as we can, so I appreciate everybody's patience, but there's lots of really good questions. Regarding the recyclability, can you just discuss what's involved in that process of recycling your materials? The comment from one of the attendees is that, in the metals industry, and frankly in plastics as well, there's some really well-known recycling methodology and processes. What does that look like for Galvorn?
Oliver, you want to take it?
Yeah, thanks, Terrence, and thanks to the questioner. It's a great question. So I think that when we share out the slides, which I think we said we would do, there's a link to some academic work done at Rice University that I was actually a part of while I was still there, where we demonstrate that you can take carbon nanotube fibers produced in that lab and put them back into the solvent, basically neat and redissolve them. And the key thing, and then respin them into new carbon nanotube fibers. The key thing and the key takeaway that I want to point out here is that unlike with other polymers in particular, you can mix different grades of carbon nanotube fiber in this recycling process and get get new carbon nanotube fiber out. So if you think about something like PET plastics, if, for instance, Dmitri has a company making PET and Terrence has a company making PET, and then you try and recycle those together, you actually can't usually do that because the PETs are slightly different enough that they'll phase separate and you won't be able to get a high quality product out of it. Carbon nanotubes seem to be very unique in this respect, and our technology in particular is able to leverage that behavior to get high quality carbon nanotubes out from the beginning. So the key enabling point for recycling our materials is that we just need to remove everything that might have been added to the fiber. So if you have it in a composite matrix, of course, that'll be a difficulty. So folks that are looking at things like thermoplastic resins rather than epoxy resins, that's really important work. Or if you chemically modify or actually do sidewall functionalization, things like that, that might cause issues.
Excellent. So one thing that occurs to me, knowing your story and listening to the presentation and looking at all the different characteristics, what we've observed over the past decade plus is that when people see what your material is capable of in terms of technical specifications, they often come up with some really new and unique applications that maybe you didn't anticipate. So I expect you'll see a lot of that because this material is really quite versatile. One of the things that you mentioned that caught my attention was also the physical mechanical properties of it and cut resistance, for example. Can you just talk a little bit more about how it resists abrasion or cutting, or what kind of tests you've done for that characteristic? I'd be curious.
Yeah, I can speak to that. So we didn't highlight this because that while this is a really unique and impressive property of Galvorn, it's not an application that we're super focused on today. We think that this is something that within the next few years is likely going to be an application that we focus on as we scale up and reduce costs. But the results that we've had for cut resistance have compared to something like Kevlar, which is known as a highly cut resistant material. We've have videos on our YouTube channel showing a friend of mine taking a big axe and swinging it onto Galvorn and Kevlar thread that is mounted on a log and basically cutting right through the Kevlar while just embedding the Galvorn into the log. And we've done more scientific testing. There's a publication with a research group in Korea that did cut resistance testing comparing Kevlar, glass fibers, Galvorn, and Galvorn basically outperformed all of them by a significant margin. So the nanotubes are somehow able to deflect this cutting force, and while under certain conditions we can cut them, a lot of the ways that are typically used to if you just take regular scissors and try to cut a thread of Galvorn, you're basically not going to be able to do it. But there are methods to cut it, so it is possible to process it. There just needs to be some adjustments that have to be made because it's such a high cut resistance material.
Interesting. Very interesting. One of the questions is, have you found any temperature dependent superconductive properties, as in a paper, they didn't refer to which one, on 1.1 degree fiber alignment? Does that question make sense to you guys?
Oliver, do you have any thoughts on that one?
I think that the end maybe doesn't perfectly make sense, but I think that no, we haven't gone searching for superconductive behavior, and some of the early work on the development of these fibers, the fibers were taken down to tens of Kelvin, and I don't think it's been exhibited.
Okay, thank you. I know that we've seen a lot of superconductivity reports, and depending on the alignment of different carbon allotropes. So I didn't know if that applied to you guys. So apologize for that question.
Oh, it's okay.
With DexMat, are you able to make films or mats from lower aspect CNTs, like the short ones or non-aligned ones? Is that another option? It sounds like your process, from what you've already said, is pretty tunable, and that you're able to use a wide variety of carbon nanotubes as raw materials, depending on what kind of attribute you want to aim for. But is there a limit? Is there a certain kind of, let me ask the question a different way. Is there a certain kind of carbon nanotube or aspect ratio that you can't work with?
I can take this one. So um, there is a limit because at some point, the way that the fibers that we make work right now in terms of strength is you are not breaking. If you take a fiber made of carbon nanotubes that are highly aligned and you do a tensile strength measurement and you pull that fiber apart until it breaks, it's not the fibers that are um, it's not the nanotubes that are breaking, it's the nanotubes slipping past each other. And it's these frictional forces that give the fibers the high strength. So when you have nanotubes that are too short, what happens is they'll just slip past each other with very little force. So at some point, when you use nanotubes that are too low in aspect ratio or too short, you're going to end up having super weak tensile properties, and at that point it becomes something that is either too difficult to handle or just not strong enough to be worth making. So that's the inherent limit is the point where they're so short that the tensile or mechanical properties are too weak.
So I assume the reverse is true. Then longer is better for that kind of tensile strength property.
Correct.
So regarding the electrical conductivity, one of the questions is, comparing Galvorn electrical conductivity to copper across all cross-sectional areas, and does it exhibit similar behavior to copper in terms of magnetic field interaction? I don't think that topic's been discussed, is the magnetic properties. Have you measured anything in that realm?
Oliver, you want to take that one?
I'm not familiar with the magnetic field behavior in specific, but I think it's something that if you reach out to us and point us to some specific measurements that would be useful, then it's something that we can look into. Are you, Dmitri?
I'm not familiar with it, no.
Yeah. Yeah, so sorry to the questioner. We're fiber spinning experts and not always electromagnetism experts, but we're always looking to learn more. And so if this is obviously magnetic behavior is super critical, we'd love to discuss the topic in depth. And I think our contact information is widely available.
I'm sure if somebody gets their hands on some of your material, they'll be doing experiments. So
Yeah.
you can count on that. What about the thermal conductivity properties of this material? So some of the advanced carbons are quite well known for their thermal conductivity in electrical applications. What about the thermal conduction properties of this Galvorn?
Why don't you take this one as well, Oliver?
Sure, that one we know a little bit more about. So the thermal conductivity, I think I mentioned the number earlier for our best fibers hovers right around where copper's thermal conductivity is. Now, because our fibers are anisotropic, meaning the structure of the fiber is different in the axial direction as opposed to the radial direction, you're going to have different properties in different directions. So I will point out that it should be lower across the side to side of the fiber as opposed down the length of the fiber. So that opens up really interesting applications in certain fields. And the other thing that we'll point out with the thermal properties, and this is not quite thermal conductivity, but kind of thermal behavior in systems, is the at a surface level, at a micron level, our fibers have a lot of surface area, and so they're able to put heat out into the environment very, very effectively. So they improve heat transfer in really interesting ways as well. So even if you have this anisotropy with thermal conductivity, you still have really great heat movement abilities because of the way it interacts with the environment.
Thank you for that. One question that often comes up with advanced carbons, carbon nanotubes, graphene, et cetera, is regarding toxicity or human health risk. Carbon nanotubes and graphene and other nanoforms of carbon can be handled very safely with proper use and processing and PPE. But regarding this material, which is finished, can you talk about any exfoliation or any of these nanotubes liberating themselves from the matrix, or anything regarding other aspects of health and safety that one might want to know about?
So in our facility, we have uh, monitors set up throughout the entire facility that are basically tracking particles that and looking to see if we have any type of nanotube content that is being uh, you know acquired on those sensors. So far, we have not seen any evidence that there's airborne carbon nanotubes that are being caught in these sensors. I think that in order to fully qualify any type of products that are going to be developed at any significant scale, there's going to be additional testing that will have to be done, and it's a product specific testing, right? Because it needs to be in the normal way of handling that product. Is there potential for release of material? So, for example, if the Galvorn is put into a composite that has a resin around it, and you're going to be, cutting that, is there a chance for release? And so, all these things still need to be studied. But so far, the evidence that we've seen is that when it's in this fiber form factor, even when you're breaking it via tensile test, there's no measurable release of material that we've been able to detect. But there's still additional testing that needs to be done that's application specific.
And
Understood.
can I add on that just to remind, we have there have been studies done on solution spun carbon nanotube fibers from a biocompatibility perspective. So if this is a really critical issue for you, again, reach out. We're happy to direct you to them. And those it was mice system studies, and no negative effects were observed. And then also in terms of skin contact, we handle made products from our fibers all the time, and we've never observed any skin irritation even. So just to kind of put a personal perspective on it.
No, thank you for that, Oliver. And there are dermal studies that have been done that, these kind of carbon allotropes are safe in terms of skin contact. Absolutely. So one of the other questions that's come up, and we'll take a few more here before we conclude, but we had so many questions, which is great because the interest is quite intense in your presentation. There was a question about whether there's any doping of the materials or functionalization, or when they're spun, are there any other materials that are basically incorporated into the product that are contributing to its strength properties, or is it really down to just the nanotubes?
Oliver, do you want to take this one?
Sure. Yeah, so it's really down to the nanotube. So we don't really use any binders or anything like that. It's important for folks who purchase our fibers to know what's in it, and it's carbon nanotubes. There is some residual solvent and processing aids trapped inside the nanotubes, perhaps, which provide electrical doping. And this ties into the kind of temperature dependence of the electrical properties I was talking about earlier. Again, we work with customers all the time to make sure that the little bit of non-carbon material that is there will work in your process. If it doesn't work with us, we can modify the material to make sure that you're getting something that has the carbon content that you desire. But yeah, the properties are purely driven. The mechanical properties are purely driven by carbon, basically van der Waals interactions between the carbon nanotube molecules, as I think Dmitri mentioned earlier.
Excellent. Thank you for that. We'll take a couple more questions here before we conclude. So one on the recycling story, which is really quite interesting. Can you speak, often when materials are recycled, the recycled material doesn't quite meet the same strength and performance characteristics of the virgin. So one of the questions is the recycled form of the material, how does that compare to the virgin form?
Yeah, you're okay if I take this one again, Dimitri? So again, the studies that were done at Rice University demonstrated that if you take carbon nanotube fibers and redissolve them and respin them, you get fibers with the exact same properties as you had after the initial spinning. And if you take carbon nanotubes produced from high quality carbon nanotubes or high aspect ratio carbon nanotubes and fibers produced from lower, but still pretty high, but lower aspect ratio carbon nanotubes, and dissolve them together and produce a new fiber, you'll get fiber with properties in between the two initial fiber properties. So it's controllable, it's well understood, it's easy, and you're maintaining properties in a manner that we can predict and expect. So this is really, really important for recyclability, and it sounds like the questioners and Terrence understand this quite well. We're not talking about downcycling. We're not talking about chopping these up and using them as a filler. You're able to take the raw material as a feed, or the finished product as a feedstock to produce new raw material, as far as we can tell so far, with the same properties as you got initially. Now, over time, we're going to be tracking how many times we can recycle this, how much those properties hold up. If we observe any degradation, we're happy to continue this work and report this out to our customer base. But it's really so far extremely exciting for us.
Excellent. Thank you for that. Again, we have over 100 people still on the line, so I'm going to take a couple more questions. If you guys are okay, we've gone 50 minutes so far. So if you stick with us just a couple more minutes, we'll take one or two more questions. There were a couple of questions asked. One asked if this material actually could be obtained in a powder form, which I found quite curious, because I think your whole raison d'etre is to turn it into a fiber and not to grind it back into a powder. But that question was asked, and also because of the high electrical conductivity, can it be made into an ink or a spray form to make a conductive coating? How do you want to react to those questions?
Well, so it's much easier to do that with the raw carbon nanotubes than it is to do that with a fiber of highly aligned nanotubes that then you would want to basically return to its original form. So I think if you want to make a spray coating, you wouldn't start with a fiber form factor. You'd start with the raw carbon nanotube materials, and likewise, the raw carbon materials, a lot of them are already in a powder-like form. So you would just start with the raw material as opposed to making into this, highly structured fiber and then trying to do that. You could potentially make it into chopped fiber, which there are some applications where it's desirable for there to be very short lengths of fiber material for obscurance and things like that. And that is something that we've had some customers that have played around with. But yeah, for those specific applications, I think you're better off not making the fiber, just starting with the raw material.
Yeah, I think there's alternative approaches to getting at that kind of a use case, as opposed to taking your highly engineered product and then deconstructing it, basically. Yeah. So one of the interesting applications that you showed, and I'll make this the last question for today, there's still a few more, but I'd encourage people to reach out to DexMat directly for additional questions and specifically about their product and applications. But on the lightning strike protection, where Galvorn can be used as a conductive fiber within that matrix, the question is, does it make the surface of the composite conductive, or does the resin in which it's encapsulated create an insulative structure? So in other words, how do you get that conductivity into the object? Is it through the fibers internally, or does it actually make the entire part from the surface down conductive? I hope that question makes sense.
You want to take that one, Oliver?
Sure. I think this would be something that would need to be kind of engineered or designed in the composite. So I think the questioner is right. If you make a composite in a standard way, you do a wet layup or something where the outside of the composite structure is essentially plastic, you're going to have that polymer inhibiting the electrical conductivity of the surface. With lightning strike protection, though, you're looking at extremely extreme electrical environments. So high temperatures, high voltages, lots of current. I don't know what would happen if lightning were to strike a outside plastic, inside carbon nanotube fiber panel. However, I would assume that at some point, very, very quickly, the polymer would really not cease to be a problem, and then the carbon nanotube interior would start taking over all of the conductivity. You can also think about in terms of engineering a material to make sure that you polish away the outside surface of the polymer so that carbon nanotube fibers are exposed on the surface, or you can engineer it so that there's actually carbon nanotube fibers that come out of the surface in different ways. I think it's a very application specific question. It's a very good question. It's something that we would have to work with folks who design those systems to make sure we're doing something that's useful for them. But the bulk of the composite will be conductive. I just can't answer how the polymer right on the outside is going to be a problem.
Understood. I mean, if we look at
Yeah.
existing lightning strike protection, there's a fine metal mesh that's laid over, and it's covered with coating, and it doesn't go directly to the air, for example. So my understanding, my very rudimentary understanding, is that with a lightning strike, it's going to penetrate the structure, but then immediately go to the protective conductive mesh that's been put on there specifically for that purpose. So I think
Great.
Probably work in the same manner.
Thanks, Terrence.
Well, gentlemen, I really appreciate your time. And first, I also want to say, congratulations to the team at Rice and to DexMat for creating this product. It's very exciting. You can see many, many uses for it. Encourage the audience, if you have questions or would like to know more information on how to use this material or get your hands on it, to please contact the guys at DexMat. Any closing comments, Oliver or Dmitri?
Yeah, I think what I'd like to wrap up with is Galvorn is going to enable us to do things in a way that's different than we do things with current materials. So one way of using it is to basically drop it in as a direct replacement for a material like copper, but also it may call for a completely different design that is not currently possible. So, for example, when they were building stone bridges, they built them one way, and then with the advent of steel, they started making suspension bridges as opposed to just making a stone bridge but using steel instead of stone. And I think similarly, Galvorn is going to enable that type of ingenuity and innovation. And so when you think about using Galvorn for applications, you need to think sometimes a little bit outside the box, and that is how you can create new truly disruptive technologies. So I think that's how I'd like to end. Thank you.
Thank you, Dmitri. Oliver?
No closing comments from me. I think Dmitri hit the nail on the head. And so I'll just say thanks again to you, Terrence, and thanks, Dmitri, for all of your insights, and thanks to everybody for coming.
Our pleasure. So the Advanced Carbon Council is very pleased to have hosted today's webinar. Thank you all for attending. Please reach out to us at the Advanced Carbons Council if you have any questions. We are a neutral, independent trade platform to help connect people looking for engineered solutions with companies like DexMat that provide advanced carbons in usable forms to solve those kind of problems. So thank you all for that. Really appreciate your time today. Take care.